Hi, and welcome back to the shop. This is part 4 of our positioning hammer project video. And today we're going to be completing the handle. Now, this is where we left off the last time. We were complete except for the taper on the handle. And well, that's what we're going to be looking at today. But we're going to be looking at it in two different ways. We're going to look at how to produce this taper using a taper attachment if you're lucky enough to have one. And if you don't, we'll be looking at how to produce it using the tailstock offset method, which is less accurate and maybe a little more daunting, but still quite doable. Now, in one case, as in the other, we're going to have to figure some things out. So let's go take a look at our drawing to determine what we're up against. If we take a closer look, we can see that our 213.3 dimension is an important one. It indicates the center of that radius. And the center of the radius, the 4.7 radius, was also the start point of the taper at its smallest diameter. However, those two dimensions, the 213.3 and the 4.7 radius, don't give me the length of the taper. You have to remember that there's a 103 millimeter long section of the handle that is knurled, and well, that knurling is clearly not part of the taper. In order to use the taper turning attachment, I'm going to have to find the half angle of this taper. Why the half angle? Well, you have to remember that on a lathe, when you turn one side of the part, you're turning the other side as well. So if I get one side of this taper to the proper angle, the other side is going to be at the proper angle. Since I've broken my taper down to a single right angle triangle, I can now calculate the angle that I need. And for that, well, I need two dimensions. I'm going to have to find the length of the taper and the height of the taper. Now, the length of the taper really isn't a problem because it's given to me on the print. The height of the triangle that I want to resolve is equal to the radius at the end of the taper, or if you prefer, 4.7 millimeters. As far as the length goes, well, I'm going to have to subtract the length of the knurled section of the hammer from the dimension of the position of that center of the radius. And that means 213.3 minus 103 millimeters, and that gives me 110.3 millimeters. So let's head over to the whiteboard and find that angle. So here's what we're up against. And this is separated into two parts. Right here on the right, well, we have what I need to calculate to find my unknown angle here so that I know at what angle to set the taper turning attachment. And on this side over here, I have what I need to calculate the quantity of offset for the tailstock if I'm using that method for producing this taper. So let's start here. I know that the triangle I want to resolve is 110.3 millimeters long and 4.7 millimeters high. To resolve this, in order to find this angle, all I have is the adjacent and opposite signs. And for that, well, I'm going to use tangent. And we're going to say tangent of the unknown angle, this one here, equals opposite 4.7 divided by adjacent 110.3. 4.7 divided by 110.3 is 0.04261. Now, that's the tan of the angle that's equal to that. What I want to know is the angle. So to get rid of my tan here, I have to multiply or divide both sides by tan, and I end up with the angle is equal to 0.04261 divided by tan. And as we've seen in our trig and triangle video on how to use all this and how to do basic algebra, well, if we want to divide by tan, we're going to multiply by the opposite, or tan exposing -1. So 10 to the minus 1 power if you prefer. And if I resolve that, I end up with an angle of 2.4399. Now don't get upset if I run through this quickly, because we do have that video that explains how to perform these mathematical operations. So we end up with this angle. Now this taper is aesthetic. It doesn't have to be deathly accurate. So I'm just going to round things off to 2.5 degrees. And on my taper attachment, on the lathe that I'm going to use for this, well, the scale is divided into minutes and seconds. And 2.5, well, it's easy to find because 2.5 in degrees, minutes, seconds would be 2 degrees, 30 minutes. And that'll be easy to set up. So 2.5 is what I'm going to use for this. Now, we know that triangles grow, if I maintain the same angles, triangles grow at a predictable rate, really at a percentage rate. So if my base here grows by 50%, well, my height here will grow by 50%, and everything stays relative. So that means that if I know what the base of this triangle is, and what the height of this triangle is, I'll know what a longer triangle height is, even if I don't know what it is, because I know what the base is. Now, how do I know the base? When I offset my tailstock on the lathe, I'm going to want to offset it the proper amount to get my 2.5 degree angle, or thereabouts. And to do that, I have to remember that I'm using the full length of the hammer. I'm not just offsetting the short tapered portion of the handle. I have to offset the whole handle. And that means that I have to calculate the quantity of offset, which is the opposite side here, for the whole length of the hammer. Now, I already know what the offset would be if my hammer handle were the same length as the taper. It would be 4.7. And I know that with triangles, everything stays proportionate. So on this side of my board here, I figured out what the opposing side would be if my hammer handle, complete hammer handle, were to be offset. Now, just the taper is 110, but the whole handle, including the taper, is 236. So I say simple cross multiplication. If 110.3 equals 4.7, if 110.3 equals 4.7, 236 will equal what? I don't know. But to do that, I do 236 times 4.7 divided by 110.3. And if I figure that out, I end up with 10.056. So 10 millimeters and 56 thousandths of a millimeter, which is great. That is the amount that I'm going to offset the tailstock on the lathe in order to obtain the proper angle on my taper. So that's what we need. This will be the taper attachment number down here. And this here, 10.10 millimeters and 56 thousandths of a millimeter, well, that'll be my offset quantity that I'm going to use for offsetting the tailstock. So let's head over to our machine and take a look. We're going to start with the taper attachment method. This taper is going to be cut between centers, so we can start by removing our 3-jaw chuck. Always make sure that your spindle bore is very clean, because a piece of dirt or a chip could really screw up your live center's alignment. So here's our live center. It's called a live center because it's mounted in the spindle and it turns with the spindle. The live center doesn't require lubrication because, like I just said, it turns with the spindle. Now this is the drive plate, and as the name implies, it's used to drive the part because, well, the live center supports the part but doesn't drive it. This plate is going to have to connect in some way with the part, and for that we're going to use a lathe dog. Before we get to that, we're going to have to finish supporting the part. And that's what this tailstock center is used for. Now this one incorporates some bearings, so it doesn't require lubrication either. I'm going to use this shim to protect the knurl, because the lathe dog that I'm about to mount, well, it uses a set screw, and well, that can really damage the knurl. So now we're mounting the lathe dog onto the part, and it's the dog that's going to connect the part to the drive plate so that we can drive the part in a positive way. If I use only the headstock center to drive the part, I really have to apply a lot of force with the tailstock center, and that, well, damages the bearings in that center. It's much easier to apply a light pressure with the tailstock and use this lathe dog to ensure that there's no slippage while I'm cutting. And as you can see here, the lathe dog leans up against the drive pin that's in the drive plate. So we're going to want to use the automatic feed for cutting this taper. That means we're going to have to set it up. The first thing to determine is the feed that we want. We're going to want to feed here around 6/1000ths of an inch per revolution. If you don't know what I'm talking about as far as feed goes here, well, you're going to want to go and watch Chips, Speeds, and Feeds Part 1 and Part 2, and well, that'll bring you up to speed. The next thing that we have to determine is the headstock's gear train setup. The headstock's gear train defines the relation between the lathe's spindle and the lathe's feed gearbox drive shaft. We can see that this machine is set up in the F configuration. So we have a 40, a 95, a 44, and an 88 tooth gear installed in that order. If I look at the feed chart on the lathe, well, I can see that in the F configuration, if I want to get 6/1000ths of an inch per rev, I'm going to have to set up at AR4X. So A, R, X, and 4. We want to feed towards the headstock when the spindle is rotating clockwise. Now we can disengage our safety switch and adjust our RPM to around 600. Now it doesn't have to be deathly accurate, 600, 620, 580, it's all good. Now we're not finished our setup, so make certain that you hit the safety switch. We can now move on to installing what's required to make this taper attachment function properly, i.e. something to lock the taper attachment's ruler in place. Once everything's nicely tightened down, you're going to want to cycle your saddle back and forth a bit just to ensure that you can reach the entire length of the taper that you have to cut. Now we're ready to start adjusting the ruler on the taper attachment, and I want it, if you remember our calculations, at 2.5 degrees or 2 degrees 30 minutes, because this ruler is divided into degrees and minutes. So I just slide it over or pivot it over with the adjustment screw, and once I get there, I lock everything in place. We can position the ruler of this taper attachment within 15 minutes of a degree, and for that we use two scales, a fixed scale that's divided in 1 degree segments, and a vernier scale that's divided in segments representing 15 minutes. As you can see, our fixed scale is divided into 10 degrees on each side of the zero. And why is that? Well, I may want to cut the taper from small to big, cutting towards the headstock, or from big to small, cutting towards the headstock. So in this case, I want to cut from small to big in the direction of the headstock. So I'll be offsetting my ruler in this direction. Now, The 0 mark on each scale is the reference or the start-off point for each scale. So if these scales were aligned at 0 on 0, well, I would have no angle. If, however, I wanted 2 degrees, well, the 0 on the vernier scale would be aligned with the 2-degree line on the fixed scale. In this case, we want 2.5 degrees, or if you prefer, 2 degrees 30 minutes. For that, we'll want the 0 of the vernier scale to be positioned about mid-distance between the 2 and 3 degree line of the fixed scale. In order to position it accurately at 2 degrees 30 minutes, once the 0 of the vernier scale aligns with the 2-degree mark on the fixed scale, we just keep moving in the same direction until the 30-minute line of the vernier scale aligns with the next line on the fixed scale that it encounters. And that means that we have 2 degrees 30 minutes. You can then lock it in that position and, well, Bob's your uncle. The next step in our setup will be to set the compound rest very parallel to the cross slide. This is crucial since all my depths of cut will be set with the compound rest hand wheel. To use most home shop taper attachments, if you have one, you're going to have to disengage the cross slide's drive nut for the lead screw of the cross slide hand wheel. So we have to disengage that so you can't use it, and that's why we're putting the compound rest at a parallel, or setting it parallel to the cross slide, so that we can use it to set our depth of cut. There is a problem, however, with backlash. Let's say that this is the block that slides along the ruler that pushes and pulls on the cross slide in order to cut our taper. Well, this block can't be tight on the ruler, or else this wouldn't work, it would seize up. And if it was just slightly snug, well, it would bounce its way down the ruler because it would grab, let go, and that wouldn't give you a very good finish. So we need some slack there, a couple of thousandths of an inch, maybe up to 4/1000ths of an inch, but we do need a little bit there. And that's fine with this because I'm cutting in this direction and I see that I'm leaning there, so as I move longitudinally, I follow the ruler from the start right to the end. However, when I change directions, I have this to contend with, and when I change directions, I come there. That first movement is parallel to the axis of rotation and will not cut a taper. From there on, it'll move at an angle, and that's fine. This direction, that's no problem, because the slack on this side moves the tool away from the part, and I don't cut in that direction. I'm only cutting in this direction. The problem comes on the second pass, because if I feed in and then go, this slack is still there, and I'll get a parallel cut before I get a taper, and my taper starts in the bottom of that 4.7 millimeter radius groove, just this side of the shoulder. So I can't sort of go by past it, come back to get rid of the looseness or the slack. I'm stuck. So what am I going to do? Well, as I come back, I'm going to feed the compound rest out far enough so that the tool clears that shoulder. I'm going to go past the shoulder, come back to where my start point is for my taper, feed in plus my next depth of cut, and that'll position me at the start of my taper, and I can take my second cut. And I'll keep doing that. That's why we're doing it in the video. You'll see I go past and come back. Now, the only other thing that needs to be mentioned here is that once you go past and come back, you can only go in and go forward. If you have to go back that direction, your slack is going to come back, so you have to back out, go past, come back, come back. So be careful for that. So let's go over to the machine and take a look at cutting that taper. We can use the same tool that we've been using up till now. However, we're going to have to knock one corner off of the tool in order to get the tool to the bottom of the groove without hitting the handle's shoulder. There, the part is set up and we're ready to go. So I'm going to feed past the start point of the taper. I'm going to come back to the start point, feed down with the compound rest hand wheel, and engage my feed. Since we've eliminated all the backlash, I know that my taper will start right off the bat. All that I have to do now is continue working with that same sequence, slowly and gradually getting the tool closer and closer to the bottom of the 4.7 millimeter radius groove. You'll know that you've reached the proper depth when the taper runs tangent into the groove. When they're both flush, well, it's time to stop cutting. As you can see here, the taper feathers out into the knurling, and that's not very pretty. So on your last cut, stop the tool before it feathers out. That'll make for a really nice, clean, crisp transition between the two surfaces. And there you go. That's one way of producing the taper. Now we'll move over to my home shop and take a look at how to do it by offsetting the tailstock. It's not uncommon to discover that we don't have all the tools required to do a certain job in the optimal way. My small home shop lathe here does not have a taper attachment, and I'm even going to pretend that I don't have a drive plate, I don't have a lathe dog, and I don't even have a live center for my headstock. The easiest thing to do here would be to just throw in the towel and not complete the project. The second easiest thing to do would be to go buy what's required to complete the project. Well, that sounds a little expensive. I, however, intend to use the third option, which is to get creative. What I'm going to do here is produce a live center, and I'm going to also incorporate into that live center a drive pin. And then all I have to do is fudge some type of lathe dog that will link the part that I'm machining to the drive pin. There, this end is complete. All I wanted here was a geometrically accurate cylinder and a shoulder. The cylindrical shape is going to be used for holding this tool, and the shoulder, well, it's going to be used as a stop to make sure that this live center doesn't creep into the 3-jaw chuck when I'm cutting the taper. There's going to be quite a bit of axial thrust here. So here's the center, and here is the drive pin that's going to replace the drive plate. So this should drive my lathe dog that's going to be attached onto the hammer handle. And you may remember that I said I don't have a lathe dog. Well, now I do. I just use this old and beat up parallel clamp, and I've pinned it. I've put a pin in it so that when it's mounted, I have it leaning up against the drive pin. So the dog's pin is leading up on the drive pin, and well, that will make everything turn in a positive fashion. Now, I want to offset my tailstock in that direction by 10.06 millimeters. An easy way to do that is to set up a reference. I have a pin here that's mounted in a 1, 2, 3 block that's clamped to the bed of the lathe. This pin is just barely leaning on the spindle of the tailstock. The tailstock is slightly snug but not tightened down, but the spindle is locked because I don't want it to move in its bore. Now what I want to do is loosen off the set screw on this side and tighten the set screw on the other side so that I'm going to push this over. How much? Well, I'm going to push it till I have a space here of 10.056 millimeters. And how am I going to do that? Well, I have a gauge block set up for that. And well, there you go. Taper attachment, tailstock offset. Two ways of producing the same thing. Now there's advantages and disadvantages. The advantage for the tailstock offset is that it's cheap and can be done in most home shops. The advantage for the taper attachment is it's much more accurate and it can be repeated. Once my taper attachment is set up, I can turn out as many tapers parts as I want. The parts don't even have to all be the same length as long as they have the same taper. More accurate because the ruler on the taper attachment can be set accurately, and I can even use a sign bar on there to get it dead on. This is obviously less accurate, but it also has the disadvantage that the total length of the part affects the angle. So each part requires a setup, even if the angle of the taper is the same. Also with this one, major disadvantage is that you have to offset the tailstock. Now if you do that, that means that you have to align it again, and that's time consuming. So overall, if you're working more professionally, well, obviously a good taper attachment is what you want. But if you're just machining for fun and don't want to go heavily into debt, well, offset the tailstock will work just fine. So until we meet the next time, have fun, be safe, and happy machining.